Can you hear me in the back, okay? Yeah, all right. Okay, so this is actually a natural sequel to a Hebert talk, and this is going to be basically a different view of the same, pretty much the same problem, or at least a similar problem. So I'm mostly a perception person, computer vision person, and the story of my life has been a little bit like this. You know, I talk to my robotics friends, and you know, they need some state-of-the-art computer vision algorithm, and I tell them about this new thing in CDPR, you know, that's like easily 4% better than last year, and you should totally use it. They try to use it, and they come back 2 weeks later saying your computer vision thing is crap, and I know that because my motion algorithm is probably correct, okay, so therefore it must be the vision system. And in fact, they are right. The reason, of course, is that, and this is related to what was said in the previous talk, we are always going to encounter failure modes in the vision system that are not properly modeled by the algorithm itself. And in particular, this is getting much worse now with the deep learning-based algorithms, which are notoriously bad at producing any kind of meaningful confidence. Again, to get back to the last comment in the previous talk. And the basic problem is if we look at the extremely simplified system like this, right? If we basically take a pipeline approach like this, we're going to essentially rely on the output of the perception algorithm to make those decisions. And more precisely, rely on some kind of confidence in those algorithms to be able to make those decisions. And this is the kind of thing where it goes really wrong. This is from a system done for the Army Research Lab on semantic navigation. So semantic navigation means, you know, you give directive to the robots in semi-natural language, like turn right after the third building, that kind of thing, which requires some semantic interpretation of the environment. So it requires actually some pretty complex, high-level understanding of the environment. So you try to do things like semantic labeling, and of course, some images are, you know, overexposed, underexposed, too close, too far, whatever, and you get completely meaningless results like this. And of course, the problem is, with those vision systems, with those algorithms, typically you can have arbitrary high, not quite arbitrary, but high confidence in fact, wrong outputs like this. By the way, this technical report here is a public technical report from ARL, from the Army Research Lab. They basically took our algorithm, put it in the field on their robots, and experimented with them, and then wrote a 100-page article on on everything that went wrong. Okay, so this is a humbling experience. You should try this at home. It's humbling. The more serious point about this is that it goes wrong a lot. Okay. In other words, there are many, many situations, and this is again going back to the point that was made in the previous talk. There are many, many situations where you actually want to ignore the output of the vision system because it cannot perform, including evaluating its own confidence. So what you really want to do is to have another thing here that basically looks at the input and knowing something about how the vision system works says, well, given this output, given those observation conditions, I'm probably not going to be able to make a sensible decision. This is very different than just looking at the output confidence of the vision system. This is learning how to guess, if you will, whether I'm in a situation where the vision system is going to perform well or not. Okay? So that's what we try to do. And again, I say we try to do because it's still in a very modest and a little bit contrived way, but I want to share with you what we try to do here. Okay? So basically, so one way to do this is to have an explicit representation of the failure cases. So we can enumerate, and there were some pictures in the previous talk, obvious failure cases, but of course that you cannot do in general because you cannot enumerate all. What you can do instead, or in addition to rather, is to have some kind of implicit representation, okay, of features from the input that are predictive of good or bad performance, okay? And in an ideal world, you would want to learn something that predicts from the input the performance of the system, okay, or the level of performance of the system, okay, as an overall end-to-end system. So if you have that, you can now make a decision as to whether you're going to actually use this output or not to make a decision, okay? Now, this sounds like a weird idea, but many people don't know about that term. You have to be old, I guess, to know about that term, okay? there's a term called declaration rate. So when you talk about detection, recognizing things and all this, you have precision recall, false positive rate, detection rate. There's actually a third axis that exists out there that's called the declaration rate. Right? Declaration rate, this is a term, by the way, that comes back like 50 years ago with the radar processing and things like this. Okay? The declaration rate basically says, what is the percentage of input on which I'm actually going to make a decision. Okay? Whether it's correct or not. Right? Whether I'm going to produce an output or not. So if you have the previous prediction of performance that I mentioned there, you can put a threshold on that prediction and say, if I'm below that threshold, I'm not going to even look at this output. Okay? I'm going to do something else. Okay? And you can vary that threshold, and you have a curve like this, right? So if the declaration rate is very, very low, you're being really conservative. You're using the output only if you're really sure that it's very good. Okay? If the declaration rate is 1, you're basically using the output all the time, and of course you're running the risk of making mistakes. So by tuning this threshold, you now have an opportunity to decide on the trade-off between, taking the risk of making a mistake, right, by having the wrong input, okay, but operating all the time, or having very low risk of making a mistake, but of course not having a lot of input from the vision system. And you can then tune in between, depending on the amount of risk that you're willing to take on the different situations. Okay. All right. So that's what we try to do. So we experimented with that on a number of different vision tasks first. So not embedded in robotic system, but separate vision tasks, things having to do with 3D estimation and object detection and things like this. And one can draw those kind of curves. So this is on one of those tasks. Doesn't matter which one. The vertical axis is the accuracy. The horizontal axis is the declaration rate. So again, 1 means I take all the inputs all the time. Even if it's complete garbage, I take all the inputs. 0 means that I'm, or close to 0 rather, means that I'm super conservative and I'm using only those inputs that I really think are going to work well for the algorithm. And so you get those kind of curves, right? The dotted one is the ideal one. And the ideal one is obtained by having an oracle that takes all those inputs and orders them according to the actual output performance. So of course that's the ideal. You cannot do that because you would have to know the actual performance on the image. And with the kind of technique that I mentioned, in other words, being able to learn that predictor, we get that pink curve here, right? Which is basically where we are now in terms of the prediction. You want to be as close as possible to this idea. Okay, so that gives you an idea of what we're trying to do here. This is another visualization of what we're trying to do. This is on a task that is not really useful for you in robotics, but is a standard computer vision task, which is a segmentation task. You take an image, and you're trying to extract the regions that correspond to the major objects in that image. So it predicts, right, after training, it predicts that the images on the left are going to be hard for that task, and the images on the right are going to be easy for that task. Okay? Now you look at this and you say, well, duh, of course. Okay? The point is to be able to do this systematically and to do this for any task, right? Being able to predict that kind of performance. This is another example now closer to robotics. This is for that semantic navigation thing, right? Where now we can predict automatically that the situations on the left are going to be hard. They're going to probably lead to poorer performance than the situation on the right, which is going to lead to higher performance. Okay? And if once you do this, you get higher performance of the entire system. Okay? So that's what we tried to do, and so those were some examples on basically offline vision example. So let's look at a more robotic example, a drone, okay, flying through dense forest kind of thing, with a single camera. Right? So it has to somehow reconstruct a coarse model of the environment, right, to be able to fly there. This is what I tell myself every morning, by the way. Anyway, so what we want to do here is again being able to predict when it is in a situation where the vision is not, the vision system is not going to perform well and may lead to degraded performance. Now, this is, of course, a critical application. Here, if the vision system fails, the planning system is going to fail, and it's going to fail in a way that is non-recoverable, typically. Now, it's a collision, and so on. So let me show you the kind of system that we use that with. Now, for those of you who are drones expert, don't laugh, okay? This is a standard system. There's nothing, exceptional about it. It's basically doing, core 3D reconstruction using an LSD SLAM-like kind of thing, right? The top left shows the color-coded depth map. The right shows the point cloud, and the way it plans is using a deliberative planner by basically doing a receding horizon type of planning by evaluating a collection of trajectories against that reconstruction. Okay? So nothing fancy about it. The main point here is that if the vision fails, everything fails, clearly. And there's no way to recover it, no pun intended, on the fly. Okay? So, the problem, of course, is that this depth estimation can be affected by many, many different factors. So, for example, lighting condition, blinded over, bad exposure, specular reflection. One thing that is not as obvious is the rotation effect. If there's a large interframe rotation, that will swarm the parallax, basically, and give poor estimate. Strong shadows, and even also uniform areas and things like this. So some of those things you could hard code, like the rotation thing. Some of those things are really difficult to hard code. I mean, what does it mean, strong shadows, exactly? Okay. So what we want to do is to learn automatically features that are predictive of performance, and we do this, of course, using. You could use any structure to learn this. We do this using a dual neural network. The neural network basically takes input from the individual image, from the monocular camera, and from the optical flow from the sequence of images. So it basically looks at what's in the image, and it looks at what's in the motion, and combines the two to predict the performance of the system. Okay? So what it actually gets out is an actual number, okay, that will be the predicted performance of the system, which I have not defined yet. Okay? So this is again the example of the input to the system. Now, of course, for this to work, and this is the critical thing in this kind of approach, right? For this to work, we have to define exactly what we mean by the predictive performance. Because if what I mean by the predictive performance is the accuracy of that point cloud, I have done nothing. Right? Because the vision system itself probably could give me some prediction of that. That's not what I want. I don't care if the point cloud is 2 millimeters accurate or 1 millimeter accurate. It's of no interest to me. The only thing that matters is whether those trajectories are evaluated correctly. Okay? So here's how we do this performance evaluation. At training time, okay, we're going to have a stereo system on the drone, which we're going to call the ground truth. It's not exactly the ground truth, but it's as good as we can get as far as the ground truth. Okay? And here, this is at the bottom here, a depiction of our trajectories, right? Green means the trajectory is free. Red means the trajectory is not free. Okay? In more elaborate thing, you would want to have some kind of, continuous thing there, but let's assume it's binary for now. Okay, just for the sake of argument. Okay? So you're going to have a discrepancy between the ground truth on the left, which says that 2 trajectories are green and 3 are red. That's how the world really is. And our perception algorithm, which says that those 2 on the left and those 2 on the right are green, and those 3 on the left are red. So in other words, something like this. So in this case, we would call the performance of the algorithm 60% accuracy. Okay? Because 60% of the trajectories are going to be correct. Okay? So in other words, the performance here is measured. Oops. Hello. The performance here is measured not on the output of the vision system, but on the behavior of the overall system. And admittedly, it's a very simple metric. Okay? So I'm not pretending that we're discovering some super elaborate metric here. But the point is that it's on the performance of the overall system. Okay? Basically, in this case, how where do I evaluate my trajectory, or more precisely, how closely to the ground truth evaluations is my evaluation of my trajectory. And that's all that matters. We don't care how accurate that point cloud is. Okay. So this is how it looks like. This is the drone flying through the woods there near CMU. And yes, if there's any government person here now, we use a tether and everything. So it's all legal, okay? So the bottom is the map, the depth map, and the point cloud on the right. What you're going to see on the right side here is a scale, okay, from 0 to 1. 0 means, so it's inverted, right? So 0 means that the data is good, we're in a good environment, meaning low probability of vision failure. 1 means very high probability of vision failure. Okay? So 1, you can think of it as 1 means that our trajectory evaluation is completely wrong, okay, or likely to be completely wrong. 0 means that our trajectory evaluation is likely to be about correct. Okay? So this is how it looks like as it goes through. Here it's fine. You see that scale is still low, and at some point, for whatever reason, it's going to be in condition it anticipates the trajectory evaluation is going to be that. So it stops at this point, moves around, okay, until it reacquires data that it feels is good enough to proceed. Now, this is the important thing here. It anticipates that situation before getting into it. Right? Gets that flow of images. It predicts that this is going to probably lead to a failure, so it stops and hovers for a while and reacquires a better thing. Okay, so one question in this kind of thing, always going back to the previous, some of the comments on the previous talk, is sorry, there's one thing I need to do here. Second here. Okay. All right. Yeah, one question that always comes up in this kind of thing is, why not use some kind of confidence that comes out of the vision system, right? And this is the example here. So this is the accuracy, and by accuracy I mean accuracy in detecting the failures. Okay. So if we get to just the confidence, we get the column on the right. If we get our prediction, we get the column on the left. Okay. And so clearly we get a higher detection. Now some of them are still called by using the confidence, the most egregious one, if you will, but many are not. Okay. And in fact, if you now look at how far you can fly, this is a very dense environment. So eventually, in fact, Emilio Ferrazzi at MIT did some calculation as to the probability of collision. Eventually, you basically guaranteed to eventually fail in that kind of test. In this kind of high density wood, without the failure prediction, we go only like about 200 meters. This is one particular configuration of the system. Right? It doesn't matter if it's state of the art or not. Really. And with failure prediction, we go 4 times further, right? 800 meters. So, and the reason is very simple, because we are able to anticipate cases where the vision system is going to fail. So it's interesting to look at reverse engineer and look at the kind of thing that it found. So those are some actual images where it automatically predicted that the vision system was going to not perform well. So things that, the things that you would expect, like overexposed scenes, rapid rotation, etc. And in fact, you can play games and try to cluster those things. So this is like an MDS mapping of those in feature space of those things, right? And you get those kind of clusters that correspond to different failure modes. So even though we don't do a explainability kind of thing where we put some kind of semantic on this, you can actually cluster this into different causes. And that actually leads to another question. I told you that once we detect those failures, we enter a hovering mode and we move around until we recover. Now that was done in that example in a completely canned motion. In other words, we stop, we move forward a little bit, sideways, up, down until it works. It would be nice to be able to predict which of those recovery maneuvers is the most likely to lead to an actual recovery of the vision system. And this suggests that it ought to be possible because those failures are clustered and for each failure, you could anticipate that a particular kind of maneuver is going to recover. So this is what we did next. And we basically said, well, we're going to try to learn. Oh, really? Okay. Oh, wow. Seriously? Okay. Okay. Okay, fine. So we try to learn how to recover those, how to schedule, if you will, those recovery maneuvers so that we maximize the probability of recovery and we minimize the time of recovery. So now not only we can detect the failure, we can try to think about how to best recover from that failure of the vision system. And the way this is done, so I'm going to maybe go a little bit faster. I don't know why I lost track of the time, but here it goes. So we basically again collect training data, right? And that training data basically consists of images or the features representing those images at different positions, and Y, which is a recovery maneuver, meaning left, right, up, down in this example, right? And then a number lambda, which is the quality measure for that recovery maneuver. So in the simplest case, lambda is either 0 or 1. Okay? 0 means by taking this action, I'm not recovering a better environment. 1 means I'm recovering. Okay, this is the simplest case. Okay, all right. So we collected data. Now there are many difficulties in doing this. One of them is you have to fly manually to do this because if you fly autonomously, you're not going to acquire enough data. Essentially, you want to be in a situation where you acquire a sufficient number of examples, okay, so that you can actually learn something from them. Basically, learn those clusters and association of those clusters to recovery maneuver. That's what it does. So at training time, we take the output of the last layer of the predictor I showed earlier, basically think of it as a feature vector, okay? And we're going to have training data that tells us, given that feature vector, I got a positive recovery or negative recovery given this action, okay? And that's going to be able to, from that, we train two predictors, one that predicts whether it's a positive action given that feature, or whether it's a negative action between that features. And taking the ratio of the two, we now have the best action to take, basically, given the input feature. Okay, so again, we fly, we get data, we extract this feature from the image, that is from our predictor, and from that feature, we can predict which one is the best recovery action to take, given that input. Okay.
So what's the difference between positive and negative?
Yeah, so this is one thing I'm skipping on a little bit. When you acquire data, the problem is if I have, let's say I move left and I recover, that's a positive data point, if you will. But it does not imply that the other maneuvers were negative. Okay, so that's why we have to train two separate classifiers, right? And then take the ratio. So think of it as those two as, you know, characterizing the distribution of the positive one, distribution of the negative one, and taking the difference. It's basically like what is called a density ratio. All right, and if you do that, you get this kind of thing where the red one is using this prediction, and the gray one is taking random action. Right, that's what you want to compare with, taking completely random action, and compare that with actually predicting what the best action to take is. Okay, and you can do this over aggregate action of the system. Okay, let's see. The last thing I want to mention very quickly, I said here that lambda is 0 or 1, meaning either we succeed or we don't. But now lambda could be continuous. Right? You could imagine lambda saying, you know, for this particular feature and this particular maneuver, I'm going to increase the performance of the system, as described before, by this amount delta lambda. Okay. So now you could imagine have a predictor now that is going to predict this increase in performance or decrease in performance. And if you do this, as you fly, you could predict from given this input, I predict that if I were to do this, it would improve the performance by this much. And if it does that enough, then you would take that decision. So you basically learn how to improve the performance of the vision system. That's basically what it boils down to. Okay. So that's what we do. I'm going to skip the details here, but basically what it boils down to is that we have the same kind of classifier as I showed, except this time instead of being a binary thing, I succeed or I don't, it's now a soft target, if you will, that tells me by how much I'm going to increase the performance. So let me skip some of those details here. Well, if you look at the delta lambda, in other words, how much a particular move would increase the performance, you basically get normally distributed things, which is very good, because that means that on average, the vision system works fine. You can't improve it that much by moving, except for some cases at the extreme, where you're going to gain a lot by applying a particular action. Right? So nominally, most of the time, you do whatever your planner would say to do, but then once in a while, you will gain a lot by doing this action. Okay? So it's basically kind of trying to characterize the performance of the overall system based on the visual input. We skip those details as well here. And then you can show that you have increase in performance. The right side here shows basically on the vertical axis the increase in that performance, right? The performance metric that I showed you, trajectory evaluation, right? Using this system over the entire flight. Okay. All right, and I want to finish since I know I'm running out of time now. I can see you nervous. Yeah, see, there's a slide number, but I don't put slide of something, right? So that's what makes you nervous, right? Okay, we're almost there. There is one comment I want to make about all this. I said earlier that a critical thing is exactly what we use as the predicted performance, right? So let me go back to this. This is the kind of thing that one does when one does things like semantic navigation, right? You want to segment the environment into semantic labels that tell you what's in the environment so you can make decisions. So obviously, the bottom one is a worse segmentation than the top one, right? Because you have this green stuff here, right? That's the shrub here in the middle of the building that's completely mislabeled. So clearly, the bottom one is worse than the top one. That's what a vision person would say. The problem with that is that when we say that, we are basically designing a vision algorithm whose loss function, whose objective function, is to minimize the number of pixels that are mislabeled, or to maximize the number of pixels that are correctly labeled. Now, there is no universe in which there is an application that requires 100% of the pixels labeled. It does not exist. Okay? So, especially for robotic application. Okay? If you think of my semantic navigation application, you don't need 100% of the pixels. Similarly, in the application I showed earlier, the flying, obviously, we don't care if the accuracy is 3 millimeter or 1 millimeter. Okay? The metric accuracy of that point cloud is of no consequence. What matters is how well we evaluate the trajectory. So the bottom line is this, that our vision system, I say that as a vision person, so I can take a hit, Our vision systems, number one, use the completely wrong metric, or loss function. Okay? And number two, worse than that, solve a problem that is much harder than the problem that we actually need. Right? So for example, labeling every pixel in an image is much harder problem, probably, than just what we need to get around the third building to the right. Okay? The important thing in all of those problems is to be able to really mathematically define that error function, that loss function, if you will, so that we can have those performance characterization and those performance prediction. Okay? And that's, in a way, the hard part. Once we can do that, then what I showed you works. Right? Once you can define that performance evaluation. All right, so, and the difficulty, of course, is that there's a number of robotic tasks that, manipulation, there's a lot of work in grasping and things like this, end-to-end learning of grasping, flying, I just showed you, with the trajectory evaluation. There's a number of those robotic tasks where you can CAN, you can define that overall performance. But then on the right, here is what I don't know how to do, is for tasks that are higher level directives, like the semantic navigation task. How do you define that overall performance? Right? That should guide, the overall estimate of system performance. So that's a big challenge, and I don't know how to do that, so I'll just put it out to you, okay? And I will stop here.
So when you're doing labeling of trajectories or how this evaluation is, are you accounting for control in external disturbance accuracy? Because if you're driving, let's say, quad over in a heavily windy conditions,
Yeah.
the quad over.
Yeah. So that's why I preface by saying that it's slightly contrived. The answer is no. And the answer is no simply because we come in from purely a computer vision standpoint. Okay. In reality, what you would want to do certainly is to have other variables input into the system. The belief, though, is that there are certain failure modes, and in fact, a large number of failure modes that are, directly linked to the vision system, independently of anything else, right? So at least we want to catch those, but certainly you want to have a much more holistic view of the system once you go to an end-to-end confidence prediction. Other questions? Yeah?
To me, one interesting part of all this is how to think about recovery, because you can have infinite failure modes, infinite ways of failing, although we talked about the delta variation at the end, but how to render policies for recovery, given that it's an infinite space.
Yeah, so that's something that we started looking at, and there's actually an interest in, now this is not well done, okay, when I'm going to say this is something that we're looking at. You can also formulate this a little bit as a bandit problem, right?
What kind of problem?
Bandits, okay, because you have kind of an infinite space, right, that you cannot explore all of it, right? So there's kind of the same kind of exploitation trade-off that you find in this problem. So we're starting to formalize that that way, right? So you want to basically have kind of an optimal trade-off between having kind of an exhaustive view of all the possible failure modes, which is not possible, right? And having the right performance. So we're looking at that kind of formalism to model those kind of expressions.
So thank you once again.